Welcome to Cybersecurity Under Pressure. Real attacks, real lessons. Every breach starts with something small. A trusted login, a missed alert, a system no one thought could matter. Here, we follow the incident. How it began, how it moved, what broke under pressure, and what security engineering and business teams should learn before the next one. Because the next attack will not wait for a perfect plan. Now, let's follow the evidence.
Welcome to Cybersecurity Under Pressure. Real attacks, real lessons.
You know, it is amazing how often we see this exact dynamic play out.
Right. I mean, imagine you just spent, let's say, $2 million building an absolutely massive earthquake-proof vault.
Yeah, to protect your most valuable physical assets.
Exactly. You pour all this reinforced concrete, you install these multi-ton steel doors, you even test it against explosives.
And you feel totally secure.
You do. But then, like a month later, you find out the manufacturer secured that impenetrable vault by buying the combination lock mechanism on clearance from a toy store.
Oh man, yeah, that is the perfect analogy for what we are looking at today.
It really is. And as we kick off the week this Monday, we're diving straight into a scenario that captures that exact modern engineering nightmare.
Because today we are looking at a situation where the physical armor of a system is absolute, but the digital foundation it stands on is suddenly violently shifting.
Right. And the central question we have to answer is this. What decision is defensible with the available evidence and real operational constraints?
That tension right there, that is the defining challenge of our era.
It really is.
And getting to the substance of that question requires us to look closely at the collision between supply chain opacity, and the absolute unforgiving necessity of keeping a physical plant running.
Because you can't just turn a plant off.
Exactly. To ground this, we are looking at a specific real-world case driven by the Siemens Product Cert Advisory. That is document SSA 86490.
Okay, so what exactly does that advisory cover?
Well, we have multiple critical vulnerabilities residing in the Fortinet next generation firewall.
And that firewall is powered by FortiOS software, right?
Yes, FortiOS software. But here is the critical twist. That software is running nested inside a piece of rugged Siemens hardware.
Oh, okay.
Specifically, the RUGGEDCOM APE Win1008.
Wow. So you have a highly critical software vulnerability buried deep inside a highly critical piece of hardware.
Right, and the threat actors are actively adapting to this. Meanwhile, the regulatory clock is just ticking loudly in the background.
The irony there is so thick you could cut it with a knife. I mean, any OT engineer, anyone managing operational technology out on the plant floor is going to feel a chill down their spine looking at this architecture.
Oh, absolutely.
Because think about it. Why do you go out and buy a ruggedized, utility-grade piece of hardware from Siemens in the first place?
You buy it for the physical resilience.
Right. You buy it specifically to protect a harsh industrial environment. We're talking about a massive electrical substation or maybe a high-volume automotive manufacturing floor.
Or a municipal water treatment facility.
Yes, exactly. You are buying it for the armor. But the cyber risk that is currently lighting up the dashboards, the thing keeping executives awake, isn't coming from the Siemens physical hardware at all.
No, it is coming from the Fortinet software running silently inside it.
Which is a terrifying realization for a plant manager or, a chief information security officer.
Because you did the procurement correctly, you audited your vendors.
Right, you checked all the boxes.
You thought you were managing a Siemens deployment. And then suddenly, on a random morning, you find out you are inheriting Fortinet's vulnerability timeline.
And these are not just minor theoretical flaws we're talking about here.
Not at all. We are dealing with alerts from CISO.
The Cybersecurity and Infrastructure Security Agency.
Exactly. Specifically, alert ICSA 2323301. And CISO is basically screaming from the rooftops that these Fortinet FortiOS vulnerabilities are actively impacting ICS environments.
Industrial control systems are directly in the crosshairs.
Yeah, so the business is caught in a vice. You have a mandate to patch a known, actively exploited threat, right?
Right.
But you face the terrifying prospect of taking down your perimeter defense and risking a plant shutdown just to apply the fix.
Technical breakdown.
So to understand what is really happening underneath, let's get into the technical breakdown.
Well, to really grasp the mechanics of this threat, we can't just look at a list of vulnerabilities.
We have to understand the asset itself, right?
Yes, the asset and the concept of the trust boundary. The device sitting at the center of this storm is that Siemens RUGGEDCOM AP18808.
I was actually looking at the physical specifications for this Siemens box before we started.
And it's pretty intense, isn't it?
Oh, it's wild. I mean, this isn't just a standard one-use server. You toss in a climate-controlled data center rack with, raised floors and a halon fire suppression system.
Far from it. This hardware platform is purpose-built for edge computing in some of the most hostile OT environments imaginable.
What kind of environments are we talking about?
We are talking about deployments where the device is literally bolted to a wall next to a vibrating turbine.
Wow.
Yeah, subjected to extreme temperature fluctuations, from sub-zero freezing cold in the winter to boiling ambient heat in a foundry.
And I imagine there's a lot of electrical noise, too.
Tons of it. It is subjected to intense electromagnetic interference, physical shock, and corrosive dust. It has to survive all of that while acting as the intelligent gateway.
So it sits right at the physical edge of the manufacturing process.
Exactly. It's the absolute dividing line.
On one side, you have the hostile, untrusted outside world. The public internet, the corporate IT network, third-party vendor remote maintenance connections.
Yeah, and on the other side.
On the other side, you have the highly sensitive, deterministic industrial control systems. These are the programmable logic controllers, the ICS devices that actually open and close the physical valves.
The devices that monitor the temperatures and run the physical plant.
Right. And that really defines the trust boundary. Everything on the inside of that APE1008 is trusted, fragile, and critical to human safety or production continuity.
And everything on the outside is a potential threat.
So the RUGGEDCOM is the literal choke point.
It is. So going back to that vault analogy you made earlier, the RUGGEDCOM hardware is the multi-ton steel door.
Right. It is doing its job physically.
Yeah, it is surviving the electromagnetic interference and the extreme heat. But the APE1008 is essentially a host.
Meaning it lets you run other software on it.
Exactly. It allows you to run commercially available cybersecurity applications. In this case, the Fortinet next-generation firewall right there on the edge.
So the Fortio software is the combination lock on the vault door.
That's it. And if an attacker can figure out how to bypass the tumblers in the software logic, the thickness of the steel door is completely irrelevant.
And looking at the evidence from FortiGuard Labs Advisory FGIR 23173, the logic has failed in several catastrophic ways.
It really has. But we have to remember, attackers do not just look at a list of common vulnerabilities and exposures, or CVEs, and pick one at random.
Right, they don't view them in isolation.
No, they view them as stepping stones.
Yeah.
They build an exploit chain. It's a journey from the outside of the vault to the inside.
So let's look at this through the eyes of an attacker mapping out that journey.
Okay, they approach the perimeter, and the first thing they want to do is test the integrity of the lock. And they find CVE 2024-52963.
Okay, and what is that one specifically?
This is an out-of-bounds write vulnerability in the FortiOS software.
So if it's out of bounds, I'm picturing data literally overflowing its designated bucket.
That's a good way to picture it.
But how does spilling data over a boundary translate to an attacker actually causing damage or taking control? I mean, what is the physical mechanism happening in the memory of that firewall?
Well, think of the system memory inside the firewall, like a massive wall of physical mailboxes.
Okay, mailboxes. I'm with you.
When the firewall receives network traffic from the outside world, the FortiOS software is supposed to look at the incoming data packet, determine its size, and allocate it to a specific mailbox.
Let's say mailbox number 4.
Right, mailbox number 4. The software is fundamentally responsible for checking that the package actually fits inside mailbox number 4 before shoving it in.
But in an out-of-bounds write, it skips that measurement step.
Yes, and that omission is fatal. An unauthenticated attacker, someone who has no username, no password, no right to be there, sends a specially crafted, maliciously oversized network packet to the firewall.
And because FortiOS fails to sanitize or check the bounds of that incoming data,
it tries to shove a massive, oversized package into mailbox number 4. The contents violently spill over, crushing the data residing in mailbox number 5, mailbox number 6, and so on.
Wow. And if mailbox number 5 happened to contain the critical instructions for keeping the operating system stable,
or the routing tables that tell the firewall where to send traffic,
then what happens?
then the system goes down in flames. In the absolute worst-case scenario for the defender, the attacker manages to overwrite memory that controls the execution flow.
So they trick the processor into executing their own malicious code.
Exactly. But even if they fail to get code execution, the mere act of corrupting that adjacent memory causes a fatal kernel panic.
The firewall process crashes entirely.
Yes. The result is a denial of service. The attacker just throws malformed packets at the perimeter from the internet, and the RUGGEDCOM's combination lock jams up and breaks.
Which forces us to pause right here and evaluate the cyber-physical consequence.
Yeah.
Because a denial of service on an IT web server is, a nuisance.
Right, you just reboot it.
But a denial of service on an industrial gateway is a potential safety incident. If CVE 2024-52963 takes the firewall offline, what is the engineering impact?
And that depends entirely on how the engineers designed the architecture to fail.
This brings up the fundamental OT concept of failing open versus failing closed.
That is the pivotal variable in risk assessment for these environments.
Because if the firewall fails open, it means that when the software crashes and burns, the device defaults to allowing all network traffic to pass through unimpeded.
The vault door basically loses power and swings wide open.
Exactly. The attacker successfully crashes the FortiOS firewall, and suddenly they have an uninspected, unauthenticated route directly into the fragile ICS network.
So the plant is entirely exposed to whatever they want to send next.
But if the engineers were focused purely on perimeter security, they might have designed it to fail closed.
And failing closed introduces a totally different kind of nightmare.
How so?
Well, if it fails closed, when the software crashes, all traffic stops entirely. The vault door slams shut, locks permanently, and drops heavy metal bars.
Which, sounds great to an IT security auditor.
Sure, but on the plant floor, it halts production. Think about it. If that APE 1108 gateway is acting as the primary conduit for critical telemetry.
Like, for example, if it is sending continuous pressure readings from a volatile chemical mixer back to a central monitoring station.
Or receiving automated remote commands to adjust a cooling fan. If the gateway fails closed, you instantly sever that data flow.
So the physical process might have to be emergency stopped, because the human operators in the control room are now flying completely blind.
Exactly. They can't see the pressure rising.
It becomes a self-inflicted outage initiated by the attacker.
And they don't even need to break into the plant to cause chaos. They just need to blind the operators.
That's terrifying. But let's advance the attacker's journey. Let's assume they don't just want a blunt force denial of service.
Right. They want quiet, persistent access to the inside of the plant. A DOS is way too noisy.
So where do they pivot?
This is where they pivot to the second vulnerability in the chain, CVE 2024-50562.
Okay, and what does that one do?
This is an insufficient session expiration flaw in the SSL VPN component.
The VPN is how remote maintenance engineers get into the plant from home, right?
Yes.
They authenticate,
Yeah.
and the system gives them a temporary pass.
Right. When an authorized user logs into the FortiOS SSL VPN portal, the firewall authenticates them and generates a session cookie.
Okay, a cookie.
You can think of this cookie as a digital cryptographic boarding pass. It proves to the firewall that the user has already gone through security, typed in their password, and passed their multi-factor authentication.
And standard cryptographic security dictates that when the user clicks log out, or after a specific period of idle time, that boarding pass must be mathematically invalidated on the server side.
It has to be shredded.
But because of the insufficient session expiration flaw, FortiOS is stamping the boarding pass, letting the engineer in. But when the engineer leaves, the system forgets to shred the pass.
Yes, the server keeps the session alive indefinitely in its memory, and this is where the attacker strikes.
So if the attacker manages to steal that active cookie,
Maybe they compromised the remote engineer's home Wi-Fi network, or they used a separate phishing attack to pull it from the engineer's laptop browser cache.
if they get it, they have a golden ticket.
Exactly. They present that stolen, unshredded cookie to the RUGGEDCOM's SSL VPN portal.
The firewall looks at it, checks its memory, sees the session is technically still valid because of the flaw, and just lets the attacker walk right in.
Completely bypassing the username, bypassing the password, and silently bypassing the multi-factor authentication prompt.
Wow, the system just believes the attacker is the trusted maintenance engineer returning from a coffee break.
Precise.
But there is a ceiling to that access, right? I mean, the attacker's now inside the vault, but they only have the specific, limited privileges of that one remote engineer.
True. They might be able to look at some read-only dashboards.
But they want total control over the gateway itself.
Yeah.
They want to be the god of the machine.
Which leads directly into the third vulnerability, and this is the real heavyweight in this advisory. CVE 2025-53744.
Okay.
This is an incorrect privilege assignment flaw, and it carries a CVSS score of 8.6.
Just to contextualize that for a moment, a common vulnerability scoring system score of 8.6 out of 10. In our world, a CVSS 8.6 in a critical infrastructure boundary device is not a let's schedule a meeting to discuss this next quarter problem.
Not at all.
That is a wake up the lead engineering team at 3 a.m. crisis.
Absolutely, because this vulnerability allows a remote authenticated attacker to escalate their privileges to superadmin.
And remember, thanks to the stolen cookie in the previous step, our attacker is now authenticated.
Right, they're inside the system as a lowly user.
So how do they leverage this 8.6 flaw? What is the specific mechanism that lets them jump from a standard VPN user to a superadmin who can rewrite the rules of reality on that device?
Well, the vulnerability exists deep within the FortiOS security fabric protocol.
The security fabric, what is that exactly?
The security fabric is designed to allow enterprise administrators to manage dozens or hundreds of Fortinet firewalls from a single centralized management console known as a FortiManager.
Ah, okay. So the firewalls periodically reach out and register themselves with this central manager to receive updates and policy changes.
Exactly.
So the attacker abuses that trust relationship.
Precisely. The attacker sets up their own malicious, rogue FortiManager instance somewhere on the internet.
Okay.
Because they are authenticated on the vulnerable firewall, they send a command that exploits the incorrect privilege assignment within the Fabric communication protocol.
So they effectively trick the local firewall running on the rogue DCOM into registering itself with the attacker's rogue FortiManager.
Yes. Once that handshake occurs, the rogue manager pushes down a policy that elevates the attacker's local account to superadmin.
They just hijack the chain of command.
They completely own the appliance. As a superadmin, they can rewrite the firewall routing rules to allow malicious traffic straight into the programmable logic controllers.
They can disable all security logging, so they become invisible to the security operations center.
They can do whatever they want.
And if that route sounds too complicated, or if the organization doesn't use the security fabric, the attacker has a backup plan built right into the advisory.
Right, CVE 2025-22862.
This is an authentication bypass, using an alternate path or channel.
Yes, and this one relies on a feature meant to make an administrator's life easier. The automation stitch component.
Automation stitches. So in FortiOS, these are designed to trigger automated scripted responses to specific events, right?
Exactly. For example, you can write a script that says, if the CPU utilization spikes above 90%, automatically send an alert email to the IT team.
But the attacker subverts the automation.
The attacker discovers they can trigger a malicious webhook action within this component.
And a webhook is just a way for one application to send automated data to another.
Right, because the authentication checks, validating who is allowed to execute that webhook or flawed, the attacker uses this alternate, unmonitored channel to force the firewall to execute commands on their behalf.
So they use the system's own automation logic to elevate their privileges and completely bypass the standard authentication front door.
When we step back and look at this entire sequence, it paints a chilling picture of modern threat adaptation.
It really does.
We aren't defending against a single isolated bug, we are defending against campaigns.
Right. An attacker observes your multi-million-dollar perimeter. They don't try to break the steel door.
No, they use the session expiration flaw to slip a harvested cookie into the lock. They step inside as an authenticated user.
And before the system can even register what is happening, they use the privilege assignment flaw to register a rogue manager and make themselves superadmin.
They have effectively bypassed the entire trust boundary, leveraging standard, commercially available exploits without ever needing to burn a highly valuable secret zero-day weapon.
Operational decisions.
With the mechanism clear, let's turn to the operational decisions.
This is exactly where the elegant, purely technical reality of software vulnerabilities slams headfirst into the messy, unforgiving business reality of running an industrial enterprise.
It really is.
Because the absolute nightmare for any board of directors or executive team is discovering that they have a massive, invisible blind spot embedded deep within their supply chain.
We have to unpack the supply chain transparency problem. This goes directly to the heart of the guidance being pushed globally by the National Telecommunications and Information Administration.
The NTIA.
Right, the NTIA, regarding the concept of a software bill of materials or an SBOM.
We hear SBOM thrown around at every security conference like it's a magic wand. But what is the fundamental philosophy behind it? Why do we need it?
Well, the NTIA defines an SBOM as a formal, machine-readable, nested inventory of the ingredients that make up software components.
Like an ingredients label.
Exactly. We often use the analogy of an ingredients label on a box of processed food. If you buy a box of cake mix, the back of the box lists the high-level ingredients: flour, sugar, baking powder, artificial flavor.
But an SBOM is far more rigorous than that.
It requires the manufacturer to go deeper. If they use artificial flavor, the SBOM requires the manufacturer of that flavoring to list their chemical ingredients.
So it creates a deeply nested, verifiable tree of dependencies.
Yes.
So why is this specific concept so critical when we are talking about the Siemens RUGGEDCOM AP18008? Why does the lack of an SBOM create a business crisis?
Because of the regulatory liability and the operational blindness it creates. Imagine you are the manager of a critical municipal water treatment facility.
Okay.
You did your due diligence. You purposely bought Siemens hardware because they are an industry titan in industrial engineering.
You trust the brand.
Yeah. You believe, implicitly, that you are running a homogeneous Siemens environment. Your security team diligently monitors the daily feeds for Siemens security advisories.
And then, on a Monday morning, CISO issues alert ICSA 23-23301.
Warning the entire industry that Fortinet FortiOS vulnerabilities are actively being exploited to target critical infrastructure.
And if that plant manager doesn't possess a detailed, machine-readable SBOM for their APE-808 gateway, they look at that CISO alert, they think, well, thank God we don't buy Fortinet, we only buy Siemens, and they delete the email.
Exactly. They go back to their coffee. They have absolutely no idea that their utility-grade, multi-thousand-dollar Siemens box is actually harboring the exact Fortinet software risk described in the alert.
They are completely fundamentally blind.
And this is precisely the systemic failure that the National Institute of Standards and Technology NIST is warning us about in special publication 800-161 Revision 1.
Which governs cybersecurity supply chain risk management.
Right. NIST emphasizes that as technology becomes more commoditized and integrated, the enterprise suffers severely decreased visibility into what they're actually acquiring.
Because without a standardized SBOM, dependency mapping relies on tribal knowledge.
You are relying on a senior engineer remembering a conversation from 3 years ago about what software the vendor uses.
That is functionally useless when a CVSS 8.6 vulnerability drops on your desk and regulators want to know your exposure within 24 hours.
The attacker knows FortiHotel is inside that physical box, but the defender doesn't.
But let's push back on the SBOM as a panacea for a moment.
Yeah.
Because simply having the inventory list is only half the battle. In fact, sometimes it creates more problems than it solves.
That's a fair point.
This is where we have to introduce the NIST VEX methodology. VEX stands for Vulnerability Exploitability Exchange. Why did NIST feel the need to invent VEX if we already had SBOMs?
It was a crucial evolution because the industry quickly realized that an SBOM in isolation can cause massive alert fatigue. It creates noise. Just because your Siemens RUGGEDCOM device happens to run a specific version of FortiOS somewhere deep in its internal architecture, it does not automatically mean that every single common vulnerability and exposure associated with FortiOS is practically exploitable in your highly specific hardware configuration.
Right, because context matters. The FortiOS software might be compiled by Siemens in a custom way that entirely excludes the vulnerable VPN module.
Or the hardware architecture of the AP811 might physically prevent the network exploit path from ever being reached by an outside packet.
But if you just blindly scan a raw SBOM inventory, your vulnerability management dashboard is going to light up like a Christmas tree with hundreds of critical false positives.
You will send your engineering teams chasing ghosts for weeks.
That is exactly the operational friction that VEX is designed to solve.
Yes. The NIST VEX implementation guidance provides a standardized machine-readable format for suppliers, in this case Siemens, to assert the actual exploitability of a vulnerability in their specific product context.
So a VEX document acts as a filter.
It takes the raw SBOM inventory data and refines it into actionable intelligence. It allows Siemens to issue a cryptographic statement saying, yes, we acknowledge we use FortiOS version 7.2, but no, CVE 2024-52963 does not affect this specific model because we disable the IPsec service at the hardware level.
It allows the defender to ignore the noise and focus on real risk.
But the terrible reality of our specific scenario today is that the VEX filter didn't save us.
No, it didn't. The ghosts are real. The Siemens Product Cert Advisory SSA 864900 explicitly confirms that the APE 1808 is affected by these FortiOS CVEs.
The vulnerability is present, the exploit path is viable, and the risk is active.
And this brings us to a massive substantive disagreement in the industry regarding how we handle the operational reality of patching in an OT environment.
Well, from an attacker-centric, evidentiary, and business challenge perspective, the required stance is entirely unambiguous.
Oh, unambiguous how?
You have strict contractual governance requirements with your upstream partners. You face intense regulatory pressure from agencies like CISU in the US and ANISU in Europe. And you have a confirmed active CVSS 8.6 vulnerability that gives a remote attacker the ability to gain super admin access to your perimeter gateway. You simply cannot leave a critical substation or a manufacturing floor exposed to a known, actively exploited threat.
So you're saying patch immediately?
Standard incident response governance dictates one clear path. This requires immediate patching. The business and regulatory impact of ignoring a critical alert is completely indefensible in a post-breach audit.
But wait.
If your plan is compromised, production is halted, and intellectual property is stolen because you willfully sat on a known patch, the legal liability and reputational damage are catastrophic.
Hold on, I have to stop you there and push back on that mindset entirely. Because what you are describing is applying a rigid IT governance model to an unforgiving OT reality.
Right.
And when you do that, the logic breaks down entirely.
How does it break down?
I point you directly to the empirical evidence in the Dragos report, OT cybersecurity, the reality of patching in industrial environments.
Okay, what does the Dragos data say?
The Dragos data proves that the standard IT playbook, the whole identify the vulnerability, schedule a maintenance window, deploy the patch, verify, is functionally useless and often dangerous on the plant floor.
Why would it be useless? If a software patch secures the perimeter against an 8.6 vulnerability, you deploy the patch to protect the asset.
Because in operational technology, continuous availability and physical safety trump absolutely everything else.
Yeah.
The RUGGEDCOM APE 1808 is not a web server.
I know it's not a web server.
It is a utility-grade device managing real-time physical processes. It handles industrial protocols that rely on precise millisecond timing to keep machinery synchronized.
Right.
If you take a raw, unverified Fortinet patch and blindly push it into the Siemens hardware, without waiting for Siemens engineers to fully validate it against their specific drivers, their custom firmware, and their thermal management systems, you have a massive probability of bricking the firewall entirely.
You are arguing that the cure is worse than the disease.
Empirically, yes. A theoretical exploit might take down the plant if the attacker is sophisticated enough. An unverified, incompatible patch will take down the plants, guaranteed.
Whoa.
If you push that patch at 2 p.m. on a Tuesday and it causes a kernel panic in the APE 1808, you immediately sever the telemetry to the power grid. You cause a self-inflicted outage.
I see your point.
You blind the operators to the physical state of the process. You didn't secure the network, you just automated your own unemployment. According to NIST Special Publication 882 Revision 2, the Guide to Industrial Control System Security, you are explicitly required to evaluate operational constraints versus security remediation. You cannot prioritize a digital software patch over the physical safety and continuity of the industrial process.
Okay, I will concede a partial point there. Applying a patch blindly without testing it against a digital twin or a real physical process is reckless.
Very reckless.
I agree that causing unacceptable operational friction like inadvertently taking down a critical substation because a firewall update caused a memory leak is a fundamental failure of risk management.
Exactly.
However, I strongly insist that waiting passively is equally indefensible.
We aren't just waiting passive.
But you cannot simply throw your hands up, cite a Dragos report, and wait passively for weeks while Siemens validates a patch, all while sophisticated state-sponsored attackers are actively adapting their exploit chains against the perimeter.
Right.
Relying on supplier dependencies as a blanket excuse for inaction is a failure of governance. We have to find a middle ground between a self-inflicted downtime event and negligent exposure to the internet.
Pressure test.
That sounds reasonable in principle, but now let's put it under real constraints of the pressure test.
This is where theory ends and we force a hard decision. Let's define the exact constraints of our scenario.
Okay, set the scene.
You are the operational security lead managing a critical, high-value manufacturing ICS environment. Let's say you are running a continuous batch process for a highly sensitive pharmaceutical product. The environment is highly deterministic. The network traffic is finely tuned.
And the cost of downtime is staggering. If the line stops unexpectedly for even 5 minutes, the entire batch is ruined, costing hundreds of thousands of dollars in lost materials.
Exactly. And now the external pressure arrives. CISO has officially flagged the FortiOS vulnerabilities.
The regulatory clock is ticking.
And you know your compliance auditors will be scrutinizing your response in the next quarter. The evidence of actual widespread exploitation in your specific pharmaceutical sector is currently incomplete, but the technical mechanism of the exploit is confirmed and trivial to execute.
And here is the binding constraint that turns this into a true engineering nightmare. Siemens has announced the vulnerabilities in document SSA 864900.
They have publicly acknowledged the severe risk to the hardware.
But they explicitly state they are preparing fixed versions. A fully validated, heavily tested, Siemens-approved firmware patch for your specific APE 1808 architecture is not yet available. It doesn't exist yet.
So you cannot patch.
You cannot patch. And per our earlier discussion, you absolutely cannot afford product downtime. You cannot take the perimeter firewall offline and disconnect the plant while you wait an undetermined amount of weeks for the patch to arrive.
But you must make a defensible decision, and you must make it right now.
Our mission in this pressure test is to select an immediate, reversible, and traceable measure that reduces the confirmed risk of these CVEs without causing unacceptable operational impact to the pharmaceutical line.
Let's systematically review the available options based purely on the evidence. Option 1. We do nothing. We formally accept the risk, document in the risk register, and wait for the Siemens patch to clear quality assurance.
Entirely indefensible, leaving the residual risk explicitly exposed to auditors and attackers when a CDSS 8.6 is actively being discussed in the wild is professional suicide.
Agreed. Option 2. We shut down the edge compute entirely. We physically or logically disconnect the APE 1808 gateway from the network until the patch arrives to eliminate the attack surface.
Operationally impossible. That violently severs the critical data flows between the plant floor and the enterprise monitoring systems.
Right. It violates our binding constraint of no product downtime.
The plant would essentially be running completely blind, and safety protocols would force an immediate shutdown of the batch process.
So we are left searching for a configuration level control. We cannot change the software code, so we have to change how the software behaves.
This is where we turn to the specific, targeted mitigation guidelines provided deep in the Siemens advisory.
For CVE 2024-52963, the out-of-bounds right that causes the denial of service and crashes the vault door Siemens provides an immediate configuration-based workaround.
What is the exact technical change they are asking administrators to make?
The advisory states that under the VPN IPsec Phase 1 interface configuration, administrators must modify the authentication parameters.
Modify them how?
They must either set the auth method PISC, which stands for pre-shared key, or they must explicitly set the digital signature auth parameter to disable.
Okay, let's put this specific control through the pressure test to see if it survives the reality of the plant floor. We have to evaluate it across 3 unforgiving criteria. Is it reversible? Is it traceable? And does it impact the physical process?
Let's test it. Is it reversible? Yes. A configuration change to the VPN IPsec parameters via the command line is entirely logical and contained.
Right. If the change accidentally causes an unexpected disruption in legitimate remote connectivity, a network administrator can immediately revert the configuration back to its previous state in seconds.
Exactly. It does not permanently alter or flash the underlying firmware.
Is it traceable?
Yes. Changing the auth method parameter will automatically generate a configuration change log within the FortiOS system environment.
Which is critical for compliance.
Right. This log can be instantly ingested by the Central Security Information and Event Management System. It creates a permanent, auditable, immutable record proving that the organization took decisive, proactive action on a specific date to mitigate the CVE.
It satisfies the regulatory clock and provides a defensible narrative for the auditors.
And crucially, does it impact the physical process?
No. And this is the deciding factor for our scenario. Modifying the authentication protocol for the remote VPN, shifting the cryptographic handshake to a pre-shared key, or disabling digital signatures only affects the external IT connections coming from remote engineers.
It does not alter the routing of standard ICS telemetry flowing through the gateway.
Exactly. It does not introduce processing latency into the real-time control loops managing the pharmaceutical patch. It operates entirely within the IT/OT boundary layer without interfering with the physical manufacturing execution systems below it.
It sounds like a perfect solution, but we have to be brutally honest about the residual risk here.
Yeah, we do.
This mitigation only addresses the out-of-bounds right. It stops the attacker from jamming the lock and causing a denial of service.
Right. It does absolutely nothing to fix the SSL VPN insufficient session expiration flaw CVE 2024-50562.
The attacker can still theoretically steal a cookie, bypass authentication, and walk right in.
Which means our decision architecture is incomplete, and it requires a secondary temporary measure.
If we cannot fix the session expiration flaw technically with a configuration change, we must address it operationally with human oversight.
Right. The incident response and network monitoring teams must immediately establish a known good baseline of active SSL VPN sessions.
They need to define what normal behavior looks like for that plant.
How many remote maintenance engineers typically log in at 2 a.m. on a Tuesday? Which IP addresses and geographic regions do those connections normally originate from? What is the average duration they stay connected before logging off?
Exactly. You cannot detect an anomaly if you don't know what normal looks like. Once that baseline is established, they must aggressively monitor the telemetry for deviations.
And more specifically, based on the threat intelligence, they must create high-priority alerts for any attempt by the local firewall to register itself to a new or unrecognized Fortinet manager instance on the internet.
That specific network behavior would be the smoking gun, indicating an active attempt to exploit the CVE 2025-53744 privilege escalation flaw.
So we have navigated the constraints and arrived at an agreement. The defensible decision in this high-stakes scenario is a consequence-driven response.
We proactively apply a verifiable, highly reversible configuration change to the IPsec VPN settings to completely eliminate the denial of service vector.
Simultaneously, we establish a strict human-monitored baseline for SSL VPN sessions to quickly detect any abuse of the unpatched session flaw.
This dual approach reduces the immediate attack paths, it provides a clearly auditable trail for the regulators, and most importantly, it preserves the operational baseline without halting pharmaceutical production.
At least until Siemens can finally deliver a fully validated firmware patch.
Key takeaways.
With the trade-offs on the table, let's bring it all together in the key takeaways.
If we synthesize everything we've explored today without introducing any new evidence, the engineering lesson is profound and highly disruptive to traditional IT thinking.
It really is a paradigm shift.
True operational resilience requires a deep, uncompromising understanding of your hardware's nested software. You simply can't just buy a rugged metal box from a trusted vendor, bolt it to the wall, and assume you are safe because it has a good brand name on the front.
No, you really can't.
As the IEC 62443-2-1 standard proves, we absolutely must shift our mindset from static, spreadsheet-based inventory counting to active, dynamic lifecycle management.
You have to continuously monitor how the software inside your hardware degrades over time.
And critically, a security control only actually works if it respects the operational timing and the unforgiving physical constraints the process is trying to protect.
Right.
If deploying a security patch breaks this physical manufacturing process, it isn't a security control.
Well, this is them.
It's just a denial of service attack perpetrated by your own IT department.
That is painfully accurate. And looking at this from the attacker and business perspective, the ultimate lesson is that supply chain opacity is the attacker's greatest asset and the defender's greatest liability. When you rely on complex third-party dependencies, when your enterprise buys Siemens hardware, but Siemens inherently relies heavily on Fortinet software, you do not just buy their product.
You inherit their vulnerability timelines.
Exactly. Their internal communication delays and their risk profile. A business simply cannot manage a risk it cannot see.
Which brings us back to the S-bomb.
This is why demanding an SBOM and filtering it through actionable intelligence using the VEX methodology is the only sustainable, scalable way to prioritize triage in a modern enterprise.
Right.
When critical patches are delayed by unavoidable operational constraints, you must have the deep visibility required to implement targeted, reversible, and auditable mitigations to protect the plant.
Ultimately, what this case proves is that while its actual security posture is entirely dependent on the software supply chain nested inside it.
Thank you for listening and starting your week with us today. The conversation continues on Wednesday. Cybersecurity under pressure, real attacks, real lessons.
You have been listening to Cybersecurity Under Pressure. Real attacks, real lessons. Real incidents leave real lessons. Stay prepared, stay critical, and keep following the evidence.